So, so I'm going to be talking about, well, I think the talk originally says 16-bit char supporting Clang and LLVM, but it's actually just more generic, slightly more generic, just generally non-8-bit byte supporting Clang and LLVM. Now, so first of all, let's just go into a bit of background. So we have this thing in C called char bit, which tells you how many bits essentially your char has. The standard basically says that a byte contains char bit number of bits. Generally, this is used to mean the number of bits in whatever your native machine type is, and therefore it means the sort of size of the minimal addressable unit. It doesn't have to be, though. I mean, you can target your C can be for some sort of slightly more abstract machine. Slightly more abstract machine where you don't where it doesn't map directly down to a machine sizes. Also, according to the C99 standard, I think the older standards as well, this is at least 8. I think possibly at the outset of C, beginning, you could get away with 7. I believe there's some really weird architectures with less, but for the most part, it's greater than 8. POSIX says that it must be 8 exactly, and the general assumption among lots of people who aren't compiler developers or working deep in systems, there's the assumption that bytes are 8 bits, and it kind of means that now, and generally everyone assumes that. And therefore it's also assumed that char bits equals 8. And lots of people write code assuming as such. So we have architectures which don't have this, where we have a char and a byte which isn't the normal, lovely 8-bit byte. And it matters to us. So it doesn't matter in general, but you wouldn't have thought it would matter because like all of the machines that everyone uses on day-to-day, your ARM chips, your x86 chips, all have 8-bit bytes, and that's all lovely and nice. However, there's lots of places where you don't have 8-bit bytes, where your minimal addressable unit isn't 8 bits. Our specific case that we run into is DSPs, but some other sort of more domain-specific processors might also have the same situation, where they don't have 8-bit bytes. Quite common for DSPs to have 16-bit bytes. That's very common. Sometimes it's a little bit weirder. 24-bit bytes is quite common in DSPs as well. Sometimes, and I've heard of architectures where you've got 10-bit bytes, which are in use now. I know of historical weirder architectures, but sort of odd-numbered bits per byte is, I think, less common now. Now, obviously, in order to support the C standard, you have to do something with your chars. You can't just pretend they don't exist and tell everyone not to use them. You have to support it in some way. It's very useful if you can use a native machine type for chars for efficiency reasons and for it's a bit more obvious what's going on and how it maps down to assembly and machine code. It's also important for, if you want to do string manipulation, if you want to use any legacy code, or any generic benchmarks and tests, it's quite useful to have like reasonably good performing char support, so native support of chars. So sort of workarounds which may work and they may be functional, they may obey the standard, may not be useful if you're benchmarking or if you want to if your programmers are using chars and then finding that, oh, actually you've put a workaround in and chars are 3 times less performant than just using integers in that place for memory accesses, then that's not very helpful. So LLVM and Clang, in theory, have support for this. LLVM IR is really, really nice. Everything is basically bit-based. So all of your integer types you define in terms of bits, all of your memory access you define pointers to things of sizes in bits. All of the generic stuff generally just deals with bits and doesn't deal with sort of bytes in any capacity. and therefore they don't really bake in many assumptions about the size of bytes. The data layout string, which is used to define the sizes of all your natively supported types, specifies everything in bits, which is useful as well. And in theory, we have this thing in Clang, which is char width, where you can just set the size of your chars, and that will affect what char bit means, and it will affect how Clang code gens for your target, or what it does in IR code generation. And in theory, you can set that to whatever size you want. So LLVM is generally very nice. It gives you quite a nice interface. The IR is very nice, but there's some places where this sort of assumption breaks down a bit. One is that LLVM IR doesn't have a void type. So in lots of places, you use an I8 star in place of your void type, and you just materialize them all over the place. That in itself isn't a problem. I mean, if you're using an I8 star for a void type, then you won't ever be able to dereference it without sort of casting it to some type that you can dereference. So in itself, that shouldn't be a problem, but it does mean we end up with I8 stars all over the place. There's also a couple of cases, for example, SROA, scalar replacement of aggregates, will sometimes introduce, or it will bitcast to I8 pointers. So you'll bitcast to I8 pointers. And a few other optimizations will also occasionally do a bitcast to an I8 pointer. The really annoying one, there are a lot of cases where in LLVM's code where there's just a hard-coded divide by 8 or multiplier by 8 of a byte size to convert it to a bit size or back. If you break the assumption and you set char bits to whatever, and you sort of make it so your bytes are not 8 bits, then you tend to trigger assertions and crashes, which is more beneficial than generating miscompilations. But it does mean that these sort of cases of divide 8 and multiply 8 by 8 need to be fixed. All of the intrinsics also use fixed width types, or sort of the key ones which you need to support to do anything useful, like memcopy, memset, memmove. They all take I8 pointers. And obviously this is also kind of, this maps quite cleanly to what the libraries expect. The libraries expect chars, and this is just an assumption that your char is I8, and therefore whenever you call memcopy, memset, memmove, you'll end up with the assumption that the pointers are all I8. So it's not a horrendous problem. It's not like you need to rewrite the entire compiler, but there's sort of bits and pieces in various places where it doesn't quite work, and you run into a few crashes, you run into a few errors. So there's been quite a lot of previous discussion about this point. You can see it sort of trends from back in 2009, where I think I first saw it mentioned, and then I mean there's some more active discussion this month about this. There's definitely people maintaining out-of-tree patches. These top 2 mailing list posts just this month were, I think, someone from Ericsson and someone working on DCPU 16, which I'm not quite sure what the architecture is, but where they have basically a set of patches which probably do basically what my patches do at the moment. But when I started making my changes, I made it based on some old patches back here, back in 2009, back in 2014 or something. So during all of these sort of mailing list posts, there have been various solutions which have been mentioned. We tried a few of them. I'll go through a few of them now. And then I'll go through what we settled on in the end. So one of the solutions, the first naive one I mentioned earlier, which is you just set char width. I've just used 16 as a value here. So one is just set your char width to 16, and in this case, you would kind of hope that everything just works, that Clang will just give you the correct char bits, it will generate IR as appropriate. LLVM won't care. LLVM just works in bits, so LLVM will handle this perfectly fine. It will get all the way through the back end. You'll end up with the right values. That doesn't work. It gets you some of the way there in that it it means that you find all the assertions which break when you try and make this change, which is quite useful because it points out what you need to fix. Clang, even with this, I don't know, I did look at the code more recently, and there have been some improvements on Clang on this front, and Clang doesn't make quite as many of these assumptions, but it still materializes I8 pointers in various places, and it doesn't help with LLVM side of things, where LLVM's made assumptions like in SROA, where it can just materialize I8 pointers. So this doesn't work out of the box, and it definitely needs some changes in LLVM. So, and I'll essentially talk about those changes a bit later because it becomes the correct solution, or the better solution. So the alternative solution, which is basically a workaround, is that you keep your, even if your target has 16-bit bytes, you lie and say it does. You say it does have 8-bit bytes. However, you then set the char alignment, so you set it so that all of your char valued things, all of your memory accesses to chars are aligned on 16-bit boundaries or whatever word bit boundaries you use. This minimizes any changes to LLVM. It means you don't run into the issues that where LLVM has assumed the wrong size, has assumed 8-bit bytes. And in theory, it should just work. You just use, you just align your bytes to 16 bits, and then essentially that means that you end up with dead space where you have a byte, and you've got some dead space where you've padded to fit it up to the 16-bit size or whatever native size. Then what you would do is in your back end, because all of your addresses would still be assuming 8-bit bytes, if you wanted to get down to a word size of 16 bits, you'd then have to halve all of your addresses. That's pretty easy. It's pretty easy for global addresses. You just halve the constant value you have. It's slightly harder for sort of any general pointer, because you might actually have to generate code to do a right shift by 1 or whatever to convert from a byte address to a word address. And then when you do a load or restore, you would actually, with your byte pointer, you'd actually load a word, and then you would mask off the top byte because you don't need it anymore, and that would give you your 8-bit value in your memory. There's some problems with this. One is obviously having to convert from byte addresses to word addresses is free in many cases, but occasionally you do actually need to generate some code to do this. You'll have to generate a shift, and that hits your performance. You have to do this change quite late in your back end because DAG Combiner and a few other optimizations do make assumptions about the size of your loads, and will do optimizations based on your pointers based on what they're loading, and that can cause miscompilations. You also have to generate some code to mask off the unwanted parts. You'll do a word load, you'll do a 16-bit load, but you only wanted an 8-bit value, and you're only operating on an 8-bit value, so you have to mask off the unwanted part or sign extend it to the full 16 bits, and then you operate on it. There's a minor issue with padding, and this is solvable, but caused me quite a lot of confusion when I was trying to implement this, which is Clang LLVM, they use I8, they insert I8 values for padding when they want to pad something. However, the I8s also have the same alignment restrictions. So if you insert an I8, you end up with a 16-bit value being inserted, which doesn't actually help with you. It doesn't pad anything. It just leaves everything still unaligned. That caused me a few issues. It basically meant that whenever you inserted padding, the sizes would be wrong, and then some special cases need to be added to the compiler to handle this more elegantly and make the padding work. If you make these changes and you do somehow end up with an unaligned address, you'll get crashes if you're lucky. If you're not and you've forgotten, there's some case where you materialize a I8 pointer, but you fail to actually halve the address to get a word pointer, you'll just miscompile and you won't notice. Another solution, this one's on the mailing list. We didn't actually try this, but it's been suggested, which is you use a fat pointer, essentially. So what this means is essentially your pointer is, well, I'm not well versed in how fact pointers work, but the impression I get is that you make your pointer completely opaque, essentially. So it means you can't sort of look into the pointer and use its underlying representation. You have to treat it as sort of an opaque box where you can only do loads and stores and things through. If you make it a fact pointer, so you make your I8 pointer a fact pointer, you keep it so that you do actually use 8-bit bytes to load. However, for every I8, so every 8-bit byte you're loading, you store the word address in the pointer, and then you also store an extra bit which tells you, when you load through that address, which of the bits you need to mask off. So essentially you'll end up doing a 16-bit load, assuming 16-bit bytes. You'll do a 16-bit load, and then you will use an extra bit which your pointer holds to tell you which of those 16 bits you actually wanted. And then you will add some extra code to mask that off to get back to your original byte that you wanted. David Chisnell's been working on this, the Cherry backend, for another purpose. They're actually using fact pointers. This is just one potential use of fact pointers. And I believe that code's pretty stable. He's maintaining a patch set to do that out of tree. There is a problem with performance because your word address has to be 16 bits, so you can address your full 64 kilowords, or your full address space. However, you also, in that 16 bits, you also need an extra bit to tell you, once you've loaded that word, which bit of the word you wanted. So you essentially need 17 bits of pointer. And the only way to do that is to either add a second word, so it becomes word address, and then an extra word which tells you which byte, or you can just, alternatively, you could cut down your address space and say, actually, I've only got 32 kilowords, and then use 16 bits and essentially just say the top 15 bits of this word address are the word address, and the bottom bit is just the byte select, or selecting the correct byte, and then it looks suspiciously like a normal pointer with some extra arithmetic added to it. So the actual solution, which we sort of ended up doing, and which basically everyone has done on the mailing list, and all the mailing list posts have alluded to, which is essentially you extend the data layout, and you say in LLVM, you just fix your well, you add an interface which tells you how wide your bytes are. So every case, I'll just get through this. Yeah, so in Clang then you would set your width of your chars to your actual natively supported byte size. You will add this byte bit width in LLVM, and then you will allow your target to specify how big its bytes are. And then whenever you see these sort of cases in your code where you've got divided by 8, multiplies by 8, or otherwise where you see an assumption where the bytes are assumed to be 8 bits, you make a call to this, or you find your data layout, you make a call to work out what the byte bit width is, and then you do the appropriate changes to take that into account. Otherwise, and a more generic change that you can make, which helps, is in many places in LLVM you will get sizes in terms of bytes rather than in bits, but you don't actually need to count sizes all the time in bytes. It's just a convenience thing. So the alternative is also you just change it so that where you say get size of this in bytes, you actually change it to get size of this in bits, and then you alter the code around it to make it work entirely in bits instead of bytes. And then that is generally more generic anyway, and more generically useful. But where you can't do that, you'd have to make use of a extra call to byte bit. This is pretty tedious. It requires lots of small changes all over the place. Everywhere this assumption's made, you have to break that assumption, and you have to sort of feed in the data layout and get the call to this function in there. So a few stumbling points I'll quickly go through, which I found when trying to implement this. So first of all, whenever you generate I8, so you have this cool get int 8 pointer type, which is used a lot in LLVM Clang. You need to replace that with get int n pointer type, and then make a call to the data layout to get the byte size. Use that correct byte size in bits to get the correct pointer type, and basically replace all instances of int 8 pointer type with int n pointer type. This sometimes requires you to sort of find the data layout in wherever it happens to be. The alternative to this would be to just keep allowing int 8 pointer type. However, in LLVM somewhere, maybe expand that in LLVM itself to a wider load and the appropriate maths to get the original I8 out. However, this seemed actually just replacing all the calls seemed like a more elegant solution, so that's what we settled on. We didn't really investigate this. Sorting out the intrinsics, so all of your intrinsics have sort of I8 star for pointer arguments. We've seen a different solution. So these have hard-coded I8 star as their pointer types. The intrinsics could just be made essentially to use any pointer types, which LLVM has for its intrinsics, which say the type is defined at runtime when you create the intrinsic instead of hard-coded when the table of intrinsics is generated. But what we did instead was we just added a new type, which is the byte type, which is actually a pseudo type, which essentially got converted to whatever the correct type was when you created the intrinsic. So either way, basically, when the intrinsic actually gets created, and all the sites where you can create a memcopy intrinsic and memset intrinsic, you would have to make another call to that function to get the byte size in bits, and then you'd feed that in to give it the correct type when you're building your intrinsics to use the correct type for the arguments. So there's the other thing, which is all of your hard-coded multiply by 8s and divide by 8s. This, in theory, is pretty simple. You just make calls to your data layout to get the byte size in every case that you call these. The trouble is there's lots of headers. For example, the ones which contain these functions, like your data layout.h, your MVTs, your EVTs, your value types that are used by your machines, all of the things which tell you how big the stores are. They all hard-code in divide by 8 to get the size in bytes of things, or the size in bits of things. So all of those need to be updated, and all of the call sites need to be updated to either query the data layout, either pass the data layout into here to use the correct sizes for the divides and multiplies, or they need to, basically all the calls need to be removed and replaced with something more generic. So this was the majority of the changes, is just changing all of these cases, feeding in the correct sizes of bytes into all of these functions, and updating all of the call sites and updating all the interfaces. And it's pretty much a mechanical change. It's just a mechanical change where you don't have any option but to sort of manually go through each of the files, look at all the call sites, feed in the correct information, get the correct byte size, and account for that. So yeah, so there's lots like this, very annoyingly. I can't remember where this is in. It's probably data layout. If you get the store size of a type, oh, it's type.h actually. If you get the store size of your type, you will have this very useful get the size in bits, which is lovely. It's nice and generic. It's only in bits. However, you'll then just add 7 to it and divide it by 8 to get it down to a byte size, which is very annoying. And this is in some header which has very few outside dependencies. This is just the generic type header, which is very sort of independent. So you need to basically feed in something to make this not 8 and it's not 7 and whatnot. A small complexity, even though your architecture may use non-8-bit bytes, may use 16-bit bytes, it's kind of quite useful sometimes to keep your ELF and your dwarf representation in 8-bit bytes, in the 8-bit byte world, so you have to handle that. And at some point you then have to sort of convert from whatever your machine byte is down to whatever your to 8-bit bytes. That's partly for the on-disk representation kind of assumes, certainly for dwarf, it kind of assumes that you have 8-bit bytes for your on-disk representation. So there's advantages. The advantages to doing this way is basically char bit. You're not lying when you in your C code. You're not giving a arbitrary value of char bit which doesn't actually match your machine. So it's a bit closer to. It's a bit more predictable, and there's minimal performance penalty. Whereas the other methods, like masking of parts of words and doubling the size of your pointers just so that you can address everything, is quite costly in performance. So, but this doesn't really cost you anything. The disadvantage mainly is just that it requires changes all over LLVM, and you have to maintain a lot of changes and keep hold of those changes. And it's made sort of rolling forward to the top of tree a humongous pain, because I have to maintain this, and there's lots of changes to generic code in the meantime. There's the other minor disadvantage, which it kind of breaks that assumption that everyone holds that your bytes are always 8 bits, but that's not as troublesome. I think if you're, for lots of systems where you're programming, for example, a DSP, you're well aware that bytes are not equal to 7 to 8 bits, so it's not quite such a bad thing for those. So the status of these. We have implemented this in a production compiler for a customer that we have who've got a DSP. There's no patches yet for the generic to make these changes generically. I know some of the people on the mailing list, there was more recent talk about other people who have similar patches, making them generic and submitting patches. I guess we should probably, I'll probably post the mailing list and see what status that's in. I need to, well, this production compiler is, I think, about 6 months or 9 months behind top of tree. So first of all, I need to rebase against top of tree, which is going to be a pain. And I need to actually tidy it up and build it into a patch set. So that's actually quite a large amount of work, I think, to do that. The other thing is I've only looked at the case we cared about, which is where our char bit is 16 bits, where our bytes are 16 bits. I made no attempt to handle the other cases. So it probably won't work where, at a minimum, it won't work where your char bit is not a multiple of 8, because of assumptions in the compiler about alignment and things. The other really key one before this is ever going to be ready for prime and in tree is to write some targeted tests. We don't really have a way of testing this easily because all of the targets in tree are sane and have sensibly sized bytes. I'm also not quite sure how to write targeted tests for this, but that's an exercise that I'll go through when I've got this close to ready to go in tree. So future work is to fix this all up and submit the patches for scrutiny and for people to pick them apart and tell me I've done everything wrong. Our plan is we have this experimental backend we've been working on, which we're trying to get upstream at the moment. And one of the changes I want to make is we want a target which has this kind of feature in tree. So I'm going to change our architecture to have 16-bit bytes. That gives us something to test against. One of the things I wasn't sure about is how we'll test this once it's in when it's in tree. And I'm hoping it might be an in-tree target for this feature if someone doesn't have a better alternative. I've not seen any suggestions for better alternative. Maybe DCPU 16 could be. And then the future work is handle char bits when they're not multiple of 8, when they're 12 or 10 or whatever weirdness you have. So that's everything from me now. So are there any questions?
I have one comment on the min set, min copy. You can't just use any pointer because that means that you could, in theory, call min copy from a char pointer to an int pointer. If you use byte pointer, your generic byte stuff, then it means that it has to be the minimum addressed, which is also set in the standard. I think the standard says it has to be a char pointer, or is it?
Yeah, I'm fairly sure it has to be a char pointer.
Which translates to the minimum addressed. So you may end up with generating code that it's not standard compliant or it doesn't even work. So
yeah. So my assumption would be that you would.
The base, that the byte size, byte type is, I think, is the right way to go.
Yes. I felt a bit bad about introducing that because suddenly LLVM doesn't care at all about chars, and then suddenly I've added something which is very dependent on C.
Well, but no, it's not. It's the minimum
Yeah.
addressable size. So I mean,
Yeah.
this is a computing concept. It's not a language concept.
Yeah.
In fact, the LLVM pointers are not really typed, so I'm not sure it would make any difference. But I would say that the byte type has a little chance to be accepted upstream. So probably it's a good idea to wait for the OPAC type pointer type basically.
Yes, I've not really looked at the opaque pointer stuff to see how this would change everything. I have a feeling it'll cause some knock-on effects, which would mean I have to rethink this. But, so that's an exercise for when I've had time to look at opaque pointers and what they're going to change.
And you already have the complex patch set. You don't want to have two complex patch sets.
Yes. I did a quick search because I've updated the compiler and I've updated most of the key interfaces, and I've got this working and it definitely works. But I've still got a few cases where I know I've got hard-coded divide by 8s in there, and I haven't yet figured out and fixed all of them. So there's I need to go back and review all the changes I've made. Okay, so yes.
How long does your patch stack match to when you have different address spaces with different minimum degrees of addressability?
Oh, so
Does
the question is basically what happens if you have pointers to, say you've got pointers to I8 in different, pointers to I8, or pointers to char, right? Yeah, pointers to chars in different address spaces which use different sizes. I don't think I can handle that.
You've got to
So-
tell the hardware designer to do something more simple.
Yeah, I mean, I did see that get mentioned in one of the mailing list posts as someone pointed out an architecture where they had two address spaces, one of which is word addressed and one of which is byte addressed, and they wanted to somehow magically have this be handled elegantly. That seems so unbelievably painful.
More elegant.
Doesn't that exist already when you've got memory mapped peripherals to a certain degree? You generally rely on the programmer to say if you're going to write into memory mapped stuff, you're generally using that peripheral.
Yeah, you
It's
guarantee
not
the
general-
alignments in the program.
It's not general purpose code that goes in that area.
Yeah, yeah. So that could be an exercise for when it becomes a problem. Okay. Yep.
The machine is 32 letters addressable. I've ignored this by just legalizing types to get rid of it, so it does strings very, very slowly.
Yes.
I don't desperately want to repeat all of this, but so do you have any idea when or if it will land upstream so I can do it myself?
No, I don't really know.
Maybe
It's
2019?
It depends. It requires stepping on lots of bits of the compiler to make the changes, and I have a feeling people won't necessarily be happy with the specific changes I've made, so it's probably going to be a bit of a slog to...
It makes the general case more harder to handle.
Yes, and I'm not quite sure, but I assume it would also slow things down a bit, that we have to sort of pull in the data layout everywhere and query it to get this information. Probably negligible, but yeah, there'll be... It's sort of I'll try and get some sort of incremental changes. Probably the first one is add this interface to your data layout and then try and gradually make the changes to other bits of the compiler. But that's sort of on a step-by-step basis. So one thing I haven't considered is what happens if you've got I32 as your byte size. I'm probably not able to handle up to that size, because you can still create I16 pointers, and I assume I will still end up creating I16 pointers in some cases. I haven't really thought about it, but that might still be a problem. You end up with an I16 pointer, but your char size is wider, and then you still have a problem. So, any more questions? Jeremy?
Will you make the AAP patch
Um, yes, I will once I've written it. So yes, so I'm going to put this in AAP, and we're going to, I don't know, I assume we might change AAP to suit this, but otherwise it will be a branch of AAP, which is our architecture. And my plan is to put the patch in there so that everyone can look at it and see it in a working architecture. And then hopefully that will be a good example of it working, and that it works and that it can work, and that it doesn't affect everyone else too much. Because, I mean, obviously I don't want to make these changes, put them in the compiler and break everyone's code, or slow everyone down horrendously. So, yeah. Yep.
Just one remark. In order to reduce the confusion, it might be better to use a decimal unit size instead of byte.
Yeah, so yeah, so actually in the code I've written, rather than using byte, I've used char. So I've just said char all over the code. That adds its own confusion. So probably something like minimal addressable unit or something would be more, would be better. I used char, but then I realized that char in the C standard means byte, and then I've got this, it doesn't really work. So yeah, so
using addressable unit size will also make it easier if you want to go for multiple address spaces.
Yes. Honestly, partly it was minimizing the, I didn't want to have to write lines where I was get minimal addressable unit size every time, so I just, I took the simple route and just used chars. But yeah, so that's probably going to be a good idea as well, because everyone does still assume that byte means 8 bits, so I'd prefer not to break that underlying assumption now. Okay. Okay. Thank you very much.